Hello once again, class, and welcome to another mock lecture. Today what we're going to be doing is tackling constructing linear equations from a few sentences of information. Now I know what you're thinking. You're thinking, Mock, isn't that just a long-winded way to say word problems? No. Instead, we're tackling constructing linear equations from a few sentences of information. Okay? Now I got about 3 categories that I want to go through, so let's go ahead and get into it. All right, so these first 2 examples are going to be about rates, particularly rates that involve time. You can see that I've underlined the word minute here because typically when we're talking about a rate, the denominator is some unit of time, miles per hour. In this case, it's gallons per minute. Maybe it's feet per second if you're looking at some kind of an acceleration or a velocity or something like that. So that's what I mean by rate. That's what I mean by like a rate type example. So here we've got a water tank can hold up to 124 gallons of water, but has initially only 4 gallons. A tap is turned on, pouring 15 gallons of water into the tank every minute. After how many minutes will the tank be full? So I'm going to go ahead and just visualize this for us a little bit. It's not a necessary step for everyone, but sometimes could be helpful. So I've drawn a tank here. Its capacity is 124 gallons, but right now there's only 4 gallons of water in it. And then we turn on the tap and we wait a little bit.
A few moments later.
And eventually it has 124 gallons, and that's considered full, right? It can't be any fuller than 124 gallons. So we want to try to figure out how long does it take to fill up this tank, right? How many minutes will it take for the tank to be full? Okay, well, when you're setting up rate type of linear equations, there's kind of a format that they all seem to take. And it's that there's an initial value, right? You're going to add that to your rate multiplied by an amount of time. And then you're going to set that equal to your final value, which in our case is 124 gallons. Now you might be wondering, why are we doing this? What's with this rate times time calculation that we have to kind of include in this form of the equation? Well, if you think about this in a tabular sense, right? Let's just kind of progress through this scenario minute by minute, just for a few minutes here. So in the left-hand column, we've got the number of minutes since the tap has been on. And on the right, we've got how much is in the tank, right? The volume of water that's in the tank. So of course, after 0 minutes, right before anything happens, there's 4 gallons initially. But then you turn on the tap, right? And every minute, 15 gallons get put into this tank. So after 1 minute, now there's 19 gallons. Right after 2 minutes, now there's 34 gallons. After 3 minutes, there's 49 gallons. And this pattern is going to repeat, where we're just kind of adding 15 to each previous value in the right-hand column. And so we can calculate how much there would be after t minutes. And it's in fact, you take the initial value, which is 4, and you add 15 multiplied by how many minutes have gone by, right? Like take this row, for example. That's 4 plus 3 times 15, right? Or I guess I should have wrote it as 15 times 3, whatever. Multiplication is commutative. 3 times 15 is the same as 15 times 3. But in any case, you're adding 45, right? This product is 45. That's why we get 49 here for the amount of water, because you're adding that initial value. So then our formula becomes initial value, which is 4 multiplied with 15t, and that's all equal to 124. And another thing that I encourage you to do when you're thinking about writing these equations is think about the unit of measure that you end up with, because the units on the left-hand side of the equation need to be the same as the units on the right-hand side of the equation. Okay, and they actually are, right? This unit of measure is gallons. This is actually a rate. It's 15 gallons per minute, but then the time unit is in minutes. So the minutes unit cancel. So you've got gallons plus gallons equals gallons, and that's true on the right-hand side. 124 represents the number of gallons. Anyway, this particular video is mostly about setting up these equations and not necessarily solving. But if you do solve this, you should end up with 8 minutes. And again, the unit of measure there is important, right? We're looking for how many minutes something takes to fill up. And so 8 is the answer that we get when you solve this equation, but that represents 8 minutes. Okay, here's another one. Let's say that Tifa has $777 in her savings account, and every month she deposits $77 into that account. Aerith has $588 in her savings account, and every month she deposits $104, right? How many months will it take for their accounts to be the same amount? So again, this is a rate. It's a dollar per month amount, right? So still time is kind of the denominator here. So first, let's calculate the kind of form that Tifa's account should follow here. So again, we've got an initial value, right? That's what this is, plus rate times time, right? So 777, that's the initial value that's already in her account. And then each month we're adding $77. And I went ahead and used M instead of T, even though I just explained how I normally use T, but I felt like M could stand for months. So I like that variable a little bit better. Aerith's account has $588 in it, but then every month she deposits $104. So her rate times time term there is 104M. And we want to figure out when these two things are the same. So we need to figure out when these two things are equal. So let's literally set these two equations equal to one another, right? So we need to solve 777 plus 77M is equal to 588 plus 104M. Right, and I'm just going to kind of go through it. I'm going to get all my M terms on one side of the equation and all my not M terms on the other side of the equation. So I moved the M's to the right and the not M's to the left and ended up with this. After doing some combining of like terms, dividing both sides by 27 gives us an answer of 7 months. So in 7 months, they should have the same amount. And one way to check is actually by plugging in 7 into this M and plugging in 7 into this M and making sure that these two values are the same. Now, I actually struggled with whether I should put percent equations in this video or not. They're relatively straightforward, but they're also kind of their own category as far as comprehension goes. Like, I think this is a little bit more involved than just your standard, rate times time plus initial values sort of format. But this is about a variety of different linear equations that we're constructing from sentences, remember? So I felt this would have a place in this video. So first, the thing about percent is that you need to understand that percent literally translates to per 100. So if I have 8%, the way that I interpret that is that's 8 per 100, or 8 100ths, right? 8 out of 100. Or if you turn that into a decimal, you get 0.08, which is honestly the way that I think about percentages. Every time I look at a percentage, I'm basically in my head, I'm thinking about, well, what percent decimal is that, right? So 8% is 0.08, right, as a decimal. Now, typically, when you first learn about percents, you typically learn about this particular proportionality where you've got some number over 100, and I went ahead and just used the percent sign over 100, is equal to the part over the whole, right? It's proportionality stuff. I'll probably do another video on specifically proportionalities sometime later in the future. But basically a proportionality or proportion is when you're setting two fractions equal to each other, which means that they reduce to the same unit fraction. Anyway, if you do some cross multiplication here, then how you would figure out 13% of 75 for this example is you'd set up 13 over 100 is equal to x over 75, right? Because we don't know what 13% of 75 is, that's what we're trying to find. That's the part. You do some cross multiplication, you get 13 times 75 is equal to 100 times x. 13 times 75 is 975. Is equal to 100x, you divide both sides by 100 and you get x is 9.75. So 9.75 then is 13% of 75 and we're done. Okay. But what I typically, I'm not going to go through, okay, we should always set up, this proportionality every time we do a percent problem. Now, there's something easier to use. It's called the percent equation. And if you turn the part, or rather the number over 100 into a percent decimal, you get this equation. Percent decimal is equal to part divided by whole. And then you multiply both sides by the whole. and this thing is your percent equation. Okay, so everything that I just explained basically leads to this. This is the form of percent type problems. This is what you need to know. So for the first example, oh, and by the way, I forgot about this. Percent decimals are really easy to find. You just move your decimal point to the left twice. So for example, 16%, you've got 16, if I write this out, you have 16.0, your decimal point's right here. Just move it 2 times to the left. So 0.16 is your percent decimal because you're dividing by 100. And since all of our counting system is base 10, dividing by 10 effectively just moves a decimal point to once to the left. So dividing by 100, right? 10 tens moves it twice to the left. So 2.4%, move the decimal twice, gives you 0.024. 87.61%, move the decimal twice. That's going to get you, that's the worst period ever. But you get 0.8761, right, as your percent decimal. So suppose you go into a store with a 35% off all items sale going on. You buy a scarf for $18.19. How much did you, quote unquote, save? Right? And I put that in quotations because my wife always tells me, oh, I saved this much money. You didn't save anything. You spent money, right, to buy this scarf. Anyway, that's a topic for another day. How much did you save? Now, I want to pause here for just a second because even though it says there's a 35% off sale going on, this amount, right, has really nothing to do with 35%. I mean, I guess 35% off equates to 65% of the original value, right? You take 100%, you take 35 off of it, you're left with 65%. So that means that this particular value is actually 65% of full price, right? So when we write our percent equation, I'm not going to use 0.35 at all. I'm going to use 0.65 because it's 35% off, meaning that 65% is what we paid. Okay, so, again, percent equation is percent decimal times whole is equal to part. So 0.65 instead of 0.35, I'm using X to be the whole because we don't know what the whole is, right? We don't know how much it was originally, is equal to 18.19. And then we divide both sides by 0.65, which gives us $27.98. That was the whole, right? That's how much that the scarf was originally. So if you want to figure out how much we saved, you're going to take $27.98, right? And you're going to subtract away $18.19, right? And essentially figure out what that is. So we're going to have to do some borrowing here. This is an 8. This is now 18. So this can be 9. So this is 7. Drop the decimal. Steal one from here. 17. Minus 8 is 9. And so we saved $9.79, approximately. I think I rounded this number here. I think that was like 0.976 or something like that. But essentially, we saved this amount, right? So how much did you save? We saved about $9 right off of this scarf. It's pretty good. Example number 2. Suppose your total at a sit-down restaurant is $37.95. Rather than calculate a tip using a specific percentage, you just pay $42, right? I actually do this a lot. I'm like, I don't want to calculate a tip. I'm just going to pay some whole amount because I like whole numbers personally. What percent tip did you give the waiter or waitress? Okay, so sometimes there's a danger in doing this because you might under tip someone. I think customarily it's like, if everything's nice, you want to tip about 15%. But then you decide, I'm not going to calculate it. I'm just going to do $42. Well, how much did you actually tip in that sense? So let's figure this out. I don't know why I put a pause button here, to be honest. Maybe that pause button was to explain what I just explained. Anyway, so here's the percent equation. Percent times whole, right, is equal to the part. But what's weird about this problem is that the part is actually bigger than the whole. Right? Our percent is going to be kind of more than 100% since we're paying more than what the bill was. Okay, so the way that I'm setting this up is I'm saying percent, which is going to be more than 100% of the whole is going to give us some increased amount. So the part is actually bigger than the whole here. Kind of weird, but you can still use the percent equation to do this. X is the percentage. We don't know what the percentage is in this case. So I used X, the variable for the percentage. The whole was 37.95, and then the part was 42. I divided both sides by 37.95 to get X by itself. And I got that X is equal to 1.107. Now, of course, we already know it was going to be bigger than 1 because we're increasing the amount. So I'm just going to basically take off the 1, right, the 1.0 part. And what we're going to be left with is 0.107. That's your tip percentage. So we tipped approximately, because I think I rounded this again, 10.7%. So actually, if the food was really good, maybe I under-tipped a little bit by doing this. So sometimes it's easier to just tip a specific amount. In fact, if I wanted to tip 15%, and you can skip this part if you want, because it's kind of another example. But I could just do 37.95, multiply that by 1.15, which is a 15% tip, and whatever that is, I don't have a calculator in front of me. That's how much I would pay. Okay, moving on to the next category. Okay, now in this one, I didn't really know what to call this, so we're just going to call this kind of other types of examples. But suppose you cut an 85-foot rope into 2 pieces, where one, that is the improper way to spell piece. I don't know what I'm thinking there. Pretend that says piece instead of pies. I must be hungry. Anyway, one piece is 10 feet more than twice the length of the other. How long is each piece? Okay, so essentially we've got a rope. We're going to cut this thing, right, where one piece is 10 feet longer than twice the first piece. So if the first piece has a length of X, the second piece has to be 10 plus twice X, or 2X plus 10, right? It's 10 more than twice the length of the first one, all right? Now we know that when we add these 2 pieces together, we should get 85 feet. So I'm going to do that, right? X plus 2X plus 10 should be 85 feet. And then we just solve this thing. So I can get rid of the parentheses because we're just adding. There's nothing to distribute. So X plus 2X is 3X. We have 3X plus 10 is equal to 85. Subtract 10, divide by 3. So one piece is 25 feet. And then the other one, if you plug in 25, right, for this X here, you're going to get 60 feet, right, is the other one. Okay, so we're going to do a few more examples kind of in class. Hopefully this was helpful. If you guys have any questions, make sure you send me an email or use Piazza. Thanks a ton for watching, and I'll see you in the next one.